Hello everyone! In this video, we will be exploring Newton's law of cooling. We'll be applying Newton's law of cooling to a problem in which we'll have to determine how long it'll take for a soda can to cool from one temperature to another. If you notice, in the box at the top left of the screen, we have a formula written. This formula here is Newton's law of cooling. If I read it out loud, it says T of t is equal to T naught minus T sub s times e to the power of negative k times t plus T sub s. Of course, to use any type of formula, we need to know what the variables stand for. Luckily, we have a list of those written right here. We see that the variable T of t on the left side, that represents the temperature of my object at time t. T sub naught represents the initial temperature of my cooling object, so the temperature that it starts at. T sub s represents the temperature of my surrounding environment. So in that case, that would be the temperature of maybe the room that I'm in, or the temperature of the fridge that I'm in, or something like that. Next, we have K. K is a cooling coefficient. It's the cooling coefficient of our object. We'll talk a little bit more about what that is in a second. T is the variable that represents the amount of time that's been spent since the initial time of 0. And note that T is measured in hours. So what is K? K is the cooling coefficient, but it's also just a constant. What we mean by a constant is it's a value that is set in stone. It doesn't change. It doesn't vary like our other variables because it's not a variable. It's a constant value. This constant value is unique to every single object. It would be very convenient if we could just say K is always equal to 5, but K is rarely equal to 5. Every single object has a different cooling coefficient. And why, you may ask, is because if I had a frozen ice cube and a frozen baseball and set them out at the same environment to cool down, we could imagine that the ice cube would cool down at a different rate than the baseball. The rate at which they are cooling can be encompassed in their cooling coefficient, and so this cooling coefficient is unique to every single object that we're cooling. For this particular example that we'll be focusing on the right, we will be cooling a soda can, and the average cooling coefficient for a soda can of the standard height 1.23 meters is about 6. Now we're ready to dive into the problem. It says, a case of room temperature soda has been sitting in a storage room for over 2 weeks. The storage room's temperature is constantly monitored and maintained at a 72 degree Fahrenheit temperature. An employee takes out one can and puts it in their ice cooler that has a temperature rating 38.5 degrees Fahrenheit. If the soda can has a cooling coefficient of K equal to 6, then how long will it take for the soda to reach a temperature of 40 degrees Fahrenheit? We are going to answer this question using the Newton's law of cooling. So of course, before using the formula, we need to establish what each one of our variables represent. I will start with T of t. T of t is the temperature of our object at any time t. I know that we are trying to figure out how long it will take. And so that's really asking me to find t. They want me to find the variable t, a time value. And we know that when we're solving any type of equation, we need to plug in what we know and solve for what we don't know. We don't know t, so I'm going to plug in everything except for t. That means I need to plug something in for T of t. I need to plug something in for T sub naught. I need to plug something in for T sub s. I need to plug something in for K. And again, once more, I need to plug something in for T sub s. Once I do that, I will be able to set up an equation that I can then solve for the variable t time. And so T of t, what is T of t? T is the temperature of the object at the time t. We don't know what the time t is, but we do know that at that time, the temperature of our soda will be 40 degrees Fahrenheit. And so that's telling us that the temperature of the object at that time is 40. So we have T sub t, we have something to plug in here. But now let's see, what should I plug in for T sub naught? So T sub naught, we know that that represents the initial temperature of the cooling object. It doesn't clearly state the initial temperature of the cooling object, but it does say that this soda has been cooling in a storage room for over 2 weeks, and the storage room was remained was maintained at a constant temperature of 72.8 degrees Fahrenheit. And we know that something in some environment where it's making contact with its surroundings is going to eventually reach the temperature of its surroundings. And so we can assume that after 2 weeks, it's pretty safe to say that this can of soda has now definitely reached the temperature of the room. So I'm going to say that the initial temperature of the soda can was 72.8. Okay, so we have some of our values, but we're not quite done yet. I also need T sub S. T sub S is the temperature of the surrounding environment, and we have to pay close attention here because there were 2 environments involved in this particular problem. We came from one environment, the storage room, and it went to another environment, the ice cooler. And so we're not talking about the environment it was in. We're talking about the environment that it's going to be cooling in. And so it'll be cooling inside of the ice cooler, which has a temperature reading 38.5 degrees. So hopefully it makes sense why T sub S is equal to 38.5 degrees. Okay, we already know that K is equal to 6. They told us that, cooling coefficient. And then last but not least, T, well, that's what we're trying to figure out. But I have everything I need. Let's just plug and chug. I'm going to plug every single one of these values into this formula here so that I can set up an equation that we can then solve for our variable T. Let's actually write this formula down here just so we can really have it right in our face to compare it. It never hurts to write things more than once. And so first I'm going to plug in T of T. We know T of T is 40, so I'm going to put a 40 here, bring down my equal sign, my parentheses, and now I need to plug in T sub naught. T sub naught, well, that's 72.8, so I'm going to replace that T sub naught with a 72.8. Now I'm going to subtract whatever T sub S is. T sub S is, of course, 38.5. Close my parentheses, times e to the negative k power, but k is really just 6, so negative 6 power, times t, we still don't know what t is, plus T sub S, which we know is 38.5. And so what do we see here? We see that we created an algebraic equation that we can now use to solve and find our variable t. What type of algebraic equation is this, though? We see that this isn't just any algebraic equation. This has the natural base e. And so I know that this happens to be an exponential equation. So hopefully we're comfortable solving exponential equations because we're going to need to be in order to approach the rest of this problem. Let's dive in. Luckily, as long as you know how to solve any type of linear equation, then you already have the skills you need to pretty much solve an entire exponential equation. There may be one step you're unfamiliar with, but I'll help you through it. So let's continue. So I'm trying to solve this equation, and I want to get the variable t all by itself on the right side of the equal sign. There's quite a few things that I need to get rid of to make that happen. I see there's a negative 6 over there with my t, there's a 38.5, there's all of this here that can be subtracted, and there's this e here. So there's quite a lot of things that we have to get rid of. Of course, we get rid of the outermost things first. I'm going to get rid of this addition. I see that 38.5 is adding to both sides of the equal sign, so I'm going to go ahead and take it away. I'm going to remove that 38.5, and I know if I do it to one side, I have to do it to the other side. I'm going to draw this line so that I can keep my work organized. What's left now on the left side of the equal sign, now that I subtracted that 38.5 on the left side, our calculator says 40 minus 38.5 is equal to 1.5. Nice, okay. On the right side of the equal sign, we have this here. This here says 72.8 minus 38.5. No point of there's no reason to continue writing it like that. So let's just subtract that using our calculator and we'll get 34.3. I still have my e right next to the group. I don't need the parentheses anymore. I still have my negative 6t. but I no longer have my 38.5 because we subtracted it to both sides. Now it's gone. And as you see, this equation is a little bit simpler than it was in its first step, but we have to keep going. I want to still peel back those layers. Let's next get rid of this 34.3. I see it's multiplying, and to get rid of multiplication, we divide. So I'm going to divide both sides by 34.3. We know if we do it to one side, then we have to do it to the other side. And poof, it's gone. I'm going to scroll a little bit so we can have a little bit more space. And I'm going to do something I don't like to do. I'm going to rewrite this information over here just so I can have some space. I see that we're running out of room down below. But so what does it say? We have this on the left side. Just going to rewrite that. It says 1.5 over 3.43. I have my equal sign. This is gone because we canceled it. So all that's left on the right side is this here. So I'll rewrite it. We have e to the negative 6t. Nice. So it's even more simple. But we still have some things to get rid of. I have to get rid of this e, and I have to get rid of the negative 6. As we see, the negative 6 and the t are both bound inside of this e, so I can't even touch either of these until I get rid of that e. So let's get rid of the e. And I mentioned earlier that there may be one step within this problem that you may not know how to tackle. This is that step. If you're familiar with the natural base e, then I assume that you're also familiar with the natural logarithm ln. ln and e are both natural, and they both happen to be inverses of one another. That being said, if I take the natural logarithmic function and plug e to any power into it, they cancel each other, and I get out just whatever my power was. Same thing goes the opposite direction. If I take the natural base e and I put it to the power of the natural logarithm of something, again, they cancel each other out, and I just get whatever was left inside of my argument. These are two pretty cool properties that we can use when dealing with the natural base and the natural logarithm. Whenever I want to get rid of an e, now we need to know we do so using the natural logarithm, because we know how inverse operations work. I know if I'm trying to solve an equation and I see addition there, well, then I need to subtract. If I'm trying to get rid of multiplication, then I need to divide, and so on. And now we know if I want to get rid of a natural base e, I need to use the natural logarithm ln. And so let's do this. The natural logarithm ln is a function, and because it's a function, things go inside of it. Let me show you what I mean. I'm going to natural log this right side, because like we said, if I natural log it, that'll make the e cancel, and then I get the natural log of e to the negative 6t. Oops, let me write this. That's on the left side, but this is still algebra. My bad, that's on the right side, but this is still algebra. If I do it to one side, I have to do it to the other. I just applied the natural logarithm to the right side, so I have to apply the natural logarithm to the left side. And the reason I want to emphasize that this is a function is because all of the time I will see students thinking that this means multiplication. It doesn't mean multiplication. I know we're used to seeing symbols next to a set of parentheses and being trained to think like, oh, that's multiplication. But function notation doesn't mean that. The same way f of x does not mean f times x. ln of e does not mean ln times e. It means that we're plugging the e inside of the ln, the same way we'd plug an x inside of the function f of x, and so on. But anyways, so this ln, why did we apply it? Was so that we could get rid of this e, and it's gone now. What's all that's left on the right side of the equal sign over here, now that the ln and e's are gone, is that power, but it's no longer a power. That's the power of the natural logarithm and the natural base. They just freed these from the power. On the left side, I have all of this, which I could put in my calculator, but I don't really want to worry about it right now. So I'm just going to rewrite it, and I'll worry about it in the last step. I don't like using my calculator in the middle of problems unless I absolutely have to, because every time we use a calculator, it rounds it a little bit more and makes our answer just not as precise as it could be, you know. And in math class, that may not be the biggest deal, but in practice in the real world, we've seen situations where it was the hugest still ever. Anyways, I'm still trying to get t by itself. There's only one more thing keeping t from being by itself on the right side. It's that -6. I see that it says -6t, which I know means -6 times t. And so I want to get rid of that -6. The -6 is multiplying, and the only way to get rid of multiplication is by division. So in order to get rid of that -6, I have to divide both sides by -6, because if I do it to one side, I got to do it to the other side. Boom, it's gone. All I have left on the right side of the equal sign is t, and all I have left on the left side of the equal sign is all of this ugly stuff. It's not pretty. We never said it was going to be pretty. I'm going to flip this around, put the t over here just so it's a little easier to look at. And it doesn't matter if it's pretty, because all of these atrocious numbers and symbols that we have right here go straight into my calculator. So I really don't care how pretty it looks, because it's not my problem. I'm going to push the buttons in my calculator, and out I will get the number. Oh, I just realized that I made a mistake. Over here we have 34.3. Yeah, when I rewrote it here, I rewrote it as 3.43. This should say 34.3, so I want to make sure that everyone goes and changes that. I'm going to erase this, and erase this, erase this, and erase this. All of those should say 34.3. 34.3. 34.3. And that's another reason why it's nice to wait to the very end to put things into the calculator, because that would have made a more drastic mistake had I calculated it earlier. Now we're going to put this into the calculator, and let's see what we get out. I get out 0.5216. We have to keep in mind that we are measuring this time in hours. So it'll take about 0.52-ish hours or so in order for this soda can to reach the temperature of 40 degrees inside of this cooler. This is a word problem, so it is nice for us to come and tie it all together with a sentence, just making sure that we know exactly what this answer over here actually means. And so I'm going to say, making sure to answer the question, how long will it take for the soda to reach a temperature of 40 degrees? I'll say it'll take about 0.52 hours for the soda to reach 40 degrees Fahrenheit. And there we have it.